Today we're going to start section 12.1, temperature and thermal energy. Notice your objectives: understand the nature of thermal energy as explained by the kinetic theory, define temperature and distinguish it from thermal energy, and then understand the process of reaching equilibrium and its application to measuring temperature, and then explain the Celsius and Kelvin temperature scales and convert between the two scales. So first of all, section 12.1, temperature and thermal energy. This unit begins a unit on thermodynamics, which prefix thermo we know means heat, and dynamic is motion, so thermodynamics is really the study of heat and how it affects other systems. And there are lots of theories early on about what makes a hot body hot. We know that when things gain heat, they tend to expand. If you have a metal rod and you heat it up, it's going to expand. Theories try to explain why that happens. Well, in the 1700s, we have the caloric theory. And that theory really just says you've got an invisible fluid that moves into a hot body. And because of that, it expanded. You really can't see heat. You can maybe see the effects of heat on a hot road, but you can't see heat itself. It's pure energy. So the fact that it was invisible made sense to them. And the fact that it goes from one object to another kind of makes it sound like it's a fluid. And if you add a fluid to something, it would take up more space. So it seemed to solve a lot of the issues they had with what happens when heat enters an object. The problem the scientists came up with, though, was what do you do with friction? Or how does it explain friction? Now, if you rub your hands together, both hands get warm, and it's not like you can just artificially generate this caloric or this invisible fluid, and they really had no way to explain how friction caused your hands to warm up, so they had to come up with a different theory. In the 1800s, they came up with the kinetic theory. And this just says that matter is made up of tiny particles in constant motion. And we've got a typo here. Matter is made up of tiny particles in constant motion. Hot objects move faster than the cold objects. So if you can think about our discussion a second ago, if you've got an object and it's got a certain amount of heat in it, the particles are going to be moving a little bit. Well, if you add more heat, then they're going to be vibrating even more and more and more. And the more they vibrate, the more space they will take. Therefore, they're going to expand. Can you explain friction with this? Well, sure. When you actually move your hands together, you're increasing the motion of the particles. Therefore, you're increasing the amount of heat they would have. In thermal energy, there's a term for you, is just the sum of the kinetic energy and the potential energy of the internal particles of a substance. So this is different than when we talked about kinetic and potential energy before. Before, kinetic energy dealt with the whole object moving, and the potential energy was relative to some reference level. Now we're talking about the particles that make up the object. So instead of a car having kinetic energy, the particles that make up the car are constantly in motion. So thermal energy, the fact that particles are continually moving. Now let's look at ways we can actually transfer thermal energy. There are 3 of them. You probably remember them from freshman year. The 3 are conduction, convection, and radiation. In conduction, the particles actually have to collide. So one particle runs in the next particle, it runs it in the next particle, and the next, and the heat just keeps moving from one end of the pole to the other end of the pole, or metal bar, or any object. So conduction requires a medium for this energy to transfer. Convection is a movement of fluids that actually carries the thermal energy. So instead of the particle just running into the next particle causing it to move, here the actual particles move and take the energy with it. And this works because as you heat things up, they typically expand. If they expand, they have less density, so they're going to rise. So lighter objects will rise, heavier ones will fall, and the whole fluid moves. If you can imagine a beaker of water, you're heating the bottom of it, that hot water is going to start rising to the top. The colder water on the top will fall to the bottom, and you have this little current forming. That's what a convection current is. So the actual fluids move. And again, since we're talking about particles, a medium is required. The third one is radiation, which is a transfer of energy without needing a medium. And this would be like electromagnetic radiation. We get the sun's energy to us, even though space is a complete vacuum. So of the 3 methods to transfer energy, the first 2, conduction and convection, require a medium, and radiation does not. And we'll demonstrate these 3 in class as well. Now let's look at the difference between temperature and thermal energy. A lot of times students get these a little confused. They're not the same terms. Temperature for gases is defined as, or is proportional to the average kinetic energy of the particles. So if you can measure the kinetic energy of the particles, and they have a large kinetic energy, they would have a high temperature. It's proportional, directly proportional. So it does not depend on how many particles you have. If you have 10 particles and the average is such that the temperature of 20 degrees is 20 degrees Celsius. If you have 100 particles and they're moving around with a kinetic energy such that they have an average that would relate to 20 degrees, it would still be 20 degrees Celsius. It doesn't matter how many particles you have. So temperature, a generic definition, is just a measure of the hotness of an object, how hot the object actually is. Thermal energy, on the other hand, is proportional to the number of particles you have. If you have two different masses, a 1 kilogram mass and a 2 kilogram mass, they're both at 20 degrees Celsius, they would both have the same temperature. However, the 2 kilogram mass has twice as much thermal energy. There's a certain amount of energy in the particles causing them to move around, and if you have more particles, obviously there's more motion, therefore more thermal energy. So if you needed to use that thermal energy for something, there'd be more available in the 2 kilogram mass than the 1 kilogram mass. So lastly for today, we'll deal with equilibrium in thermometry. We know that heat energy travels from hot to cold. We'll witness this in our demonstration on conduction. You put a metal bar on a hot plate. The heat's going to go from the side that's on the hot plate, and then the other side will eventually get warmer as the heat travels from hot to cold. Objects in thermal equilibrium are said to be at the same temperature. So if you're in thermal equilibrium, there's no net flow. One end is 20 degrees, the other end is 20 degrees. Energy is really not going to have a net flow from one end to the other. Just like a mass in equilibrium has no net force acting on it, it's going to just sit there. Now, just because they're at the same temperature or same thermal equilibrium, they may not have the same thermal energy. The only way they would have would be if they were made of the same material and they're at the same temperature. So the type of material affects thermal energy as well as the mass. I think I said that wrong. Type of material and mass. We know they're the same temperature. So let's look lastly at some different temperature scales. In science, we measure in Celsius degrees, but the SI unit is Kelvin, so to convert from Celsius to Kelvin, we need to add 273 degrees. To convert from Celsius to Fahrenheit, what you'd have to do is take your Celsius temperature times 1.8 and then add 32 to that. That would give you Fahrenheit. So you should be able to convert from any temperature scale. We'll do a couple examples here in a second. There are some temperatures that you should just know without having to convert, and that's what we're going to do right now in a little chart for you. So make a chart with 3 columns. This is freezing point, and this would be for just water. Boiling point of water, and then your normal body temperature. We should know what this is in Celsius for the freezing and boiling point. We know water freezes at 0 degrees Celsius and boils at 100. and normal body temperature is 37 degrees Celsius. So if you had to convert this into Kelvin, all you would have to do is take your Celsius degrees, plug it in here, add 273, and you would get 273 Kelvin for the freezing point. You can do the same thing, take your 37 degrees, plug it in there, add it to 273, and you would get 310 Kelvin. And obviously 100 plus 273 is 373 Kelvin for the boiling point. We know that water in the Fahrenheit scale freezes at 32 degrees, boils at 212 degrees, and normal body temperature is 98.6. So again, these are things you should just know. You shouldn't have to convert. And lastly, absolute zero. We know that as things heat up, they move faster. So as they cool down, they're going to get slower and slower. And if you can imagine, getting it completely cold gets slower, slower, slower. Eventually, it is so slow that the particles stop moving. And that would be absolute zero. The temperature at which an ideal gas has no volume, because our assumption is gas particles have no volume. The sample just takes up the space of the container. And if there's no motion, there's going to be no thermal energy, which would be zero on the Kelvin scale. So let's try a couple quick examples. If it's 22 degrees Celsius outside, to find Kelvin, all you would do is add those, and the Kelvin would be 295 K. Notice we don't put degrees with the Kelvin units, it's just 295 K. Or if it's 498 Kelvin, now to figure out the Celsius temperature, all you would have to do is subtract 273 from both sides, and your Celsius temperature then is 225 degrees Celsius. As far as Fahrenheit goes, your degrees Fahrenheit is your Celsius temperature times 1.8, or some books say times 9/5, and then you add 32 degrees to it. So if it's 25 degrees Celsius, what would that be in Fahrenheit? Well, 25 times 1.8 plus 32. You take out the calculator. .5 times 1.8 is 45. Add 32 to that, you get 77 degrees Fahrenheit. So a nice warm summer day. Conversely, if it's 55 degrees Fahrenheit and we want to figure out Celsius, first thing you have to do is subtract 32 from both sides. That gives me 23 equaling Celsius times 1.8. And and then divide both sides by 1.8. And when you do that, you get around 13 degrees Celsius.